Okay, good morning. My name is Michael McMahon. I'm from the Java Core Libraries team at Oracle, and I'm going to be talking to you today about the new HTTP client API that we're developing for Java. So first, to get this disclaimer out of the way, which we have to include all the time. So this presentation is for information purposes. There's no commitments to produce anything. It should be taken from this presentation. Okay, so this is the agenda. So basically I'm going to cover these 3 or 4 topics. First of all, I'm going to just give a brief introduction to HTTP2 and then go over the similarities and differences between it and HTTP 1.1. And then I'll give a quick introduction to the Completable Future API, which is quite, this HTTP API makes significant use of it. Then we'll go into the HTTP API itself, and finally then I'll do a little bit about the Flow API, which the HTTP API makes use of, but it's sections 3 and 4 are more or less the same topic. Okay, so straight into the first section. So HTTP2, what are the similarities first of all? Well, if you consider HTTP as a service or an API, then HTTP2 is pretty much the same as HTTP1. In particular, the request methods, get, post, put, delete, etc., they all have exactly the same meaning in HTTP2. Request and response headers, like content length, cookie, content encoding, they all have exactly the same meaning in HTTP2 as in HTTP1. It also has exactly the same request and response structure. A request-response exchange comprises a single request, potentially a number of intermediate responses, though usually none, followed by a final response. And then also you have request and response body data. Depending on the request method, requests or responses can have associated body data associated with them. So that's all exactly the same. So what's different? Well, the biggest difference obviously is the protocol. It's completely different, not backwards compatible at all, except insofar as a mechanism has been defined to allow an upgrade from an existing HTTP 1.1 connection to HTTP 2. But otherwise, the protocol is totally different. And the biggest difference probably is the way that HTTP 2 multiplexes multiple requests onto the same TCP connection, while avoiding the head-of-line blocking problem that HTTP 1.1 pipeline requests had. So just to explain what that means, with a little illustration. So with 1.1, if you send 3 requests, as shown here, request 1, 2, and 3, on the same TCP connection in sequence, then the responses must come back in the same order. So response 1 must come back first, then response 2 and 3. And what happens if response 1 takes a significant amount of time to generate? Well, that's too bad. Response 2 and 3 just have to wait until that happens. So HTTP2 deals with that problem by basically having a very thin layer, framing and streaming layer on top of TCP, and I'll just describe a little bit, give you an overview of that. Each request and response interaction is given its own stream, and each stream is uniquely identified by a number. And you can see there, requests 1, 2, and 3 have been given stream IDs 3, 5, and 7. So all frames, all messages associated with the stream have a stream ID, so they're identifiable. And streams are also independently flow controlled, so that's a significant point as well, which we'll come on to later. So you can see here in this example, it's possible to send back response 2 first, then response 3, and then response 1. So that avoids this whole head-of-line blocking problem that you would have seen with HTTP 1. So what else is different? Well, cancellation. It's possible to cancel requests efficiently. Now that was possible with 1.1, but only at the cost of closing the TCP connection, which obviously means you incur the overhead of reopening a TCP connection for following connections or following requests. But in HTTP2, there's an explicit mechanism for resetting one stream on a connection independently of the others. But probably the most interesting feature of HTTP2, and it's really the only one with a noticeable footprint in terms of API, is server push. And this allows servers to push resources directly into a client's cache. Now, it's not a generalized push mechanism. Its pushes are always in the context of a request that had been initiated by a client. So a server will only push resources that it knows the client or strongly suspects that the client is going to ask for anyway. And we'll see the primary use cases for that later on. What else is different? Maybe smaller features. HTTP2 allows you to prioritize requests, so they can be given a weighting relative to each other. You can express dependencies between different requests. It's quite an elaborate scheme. It remains to be seen how widely used that becomes. Then there's also a simple keep alive mechanism based on ping frames. And thirdly, a very significant feature is header compression. There is a specification called HPAC, which defines how headers are compressed. It's quite a complex system, but it's defined in such a way that receivers or decoders of headers can be implemented fully compliant and relatively easily, whereas encoders have a wide variety of different strategies that they can employ, but it's from relatively simple encoding and compression techniques to somewhat more complicated. And finally, probably a significant difference is the fact that HTTP2 is a binary protocol, whereas if you're probably familiar with traditional HTTP, it's based on ASCII strings with carriage return line feeds, that kind of thing. So what that means is, if you're debugging a HTTP connection, you won't be able to just look at a hex dump and figure out what's going on. Particularly with respect to HPAC, it's impossible to understand just by looking at the bits what's going on with HPAC. You're going to need tools to be able to decode HTTP2 headers. Let's just take a quick look at the HTTP2 frame structure. Each frame comprises a fixed 9-byte header, followed by a frame-specific payload. So those 9 bytes are, the first 3 bytes are a length field, so you have 24 bits of length. Then you have a type field of 8 bits. Now I think there are only roughly 10 frames defined at the moment, so there's plenty of headroom there. And then there are 8 bits allocated for flags. And again, I think only each frame type specifies whatever flags can be employed with each with that frame, and I think only up to the maximum number of flags that are used is 3, I think. And then finally, the final part of the header is the stream ID, which it uses 31 bits of the last 4 bytes. Stream IDs themselves, as you saw earlier, for client-initiated streams, they're always odd numbers, starting at 1 for the first request sent on a connection. Each successive request increments the last used stream ID by 2, so it goes 1, 3, 5, 7, 9, etc. And for server-initiated streams, for server pushes, they use even numbers starting at 2, so 2, 4, 6, 8, etc. So let's take a look at a simple interaction, a request and a response in terms of frames. So on the top there, we have a request sent from the client to the server, and it comprises a headers frame. So every request begins with a headers frame. If all of the headers don't fit in the headers frame, then there may be 0 or more continuation frames, but they're optional. And then if the request contains body data, then that will be followed by 1 or more data frames. And you can see there, this is that because data is flow controlled, the server needs to send window updates if there's going to be quite a significant amount of data. A sliding window flow control scheme is used, quite similar to the one used in TCP. So that's how the server regulates the amount of data that the client is sending to it. And you can see then from the response that the response uses exactly the same frames, but just sent in the opposite direction. So the other frame types, which I won't go into in any detail, except maybe for push promise, these are the other frame types which are mostly self-explanatory, except maybe settings. Settings frames are exchanged at the beginning of a connection in order to establish the parameters such as buffer sizes and flow control window sizes, that kind of thing. But I think the other frame types are probably self-explanatory. So just to maybe show a comparison of a request with between HTTP 1.1 and how the same request would look in HTTP 2. On the left-hand side, we have the traditional, familiar-looking HTTP 1 request. So what we have is a get of slash resource with two headers, host and accept. So how does that look then in HTTP 2? Well, in this case, we have a single headers frame, and it has two flags set, the end stream and the end headers flags. End stream signifies that this is the final frame sent by the client on this particular stream. So there are no more frames to follow this one, and that's simply because it's a request with no request body. And the end headers flag is set to signify that all of the headers are contained in this frame, or at least there are no following continuation frames. You can see also the same two headers, host and accept. Header names are always lowercase in HTTP 2. That's one significant feature. And then you can also see that the meta information that was encoded on the request line in HTTP 1 is encoded using special, what are known as pseudo headers in HTTP 2. And these are headers with predefined names that always begin with a colon character. So what does the response look like? So let's say on the left-hand side we have the traditional HTTP 1 response, which is a 200 OK with two response headers, content type and content length, and then followed by 123 bytes of binary data. So in this case we have a headers frame with this time only one flag is set. The end stream flag is not set because this is not the final frame of the stream from the server. But the end headers flag is set because all of the headers are contained in this frame. So we see the same content type, content length, and then a pseudo header signifying the status code, which is in :status. And then following this is a single data frame with the 123 bytes of data, and this frame has the end stream flag set. So you can see it's a very tightly defined protocol. There's not really much room for ambiguity with HTTP 2 in the way that sometimes was possible with HTTP 1. Let's take a quick look at server push then. At a high level, how does that work? So if a client issues a request, in this case, this example I'm saying it requests a resource, foo.html from the server. So the server receives the request, and it looks inside the resource, the foo.html, and it sees, okay, there are 3 references inside that HTML file to resources that also exist on this server. So the client is probably going to need those resources, so I'm going to push those resources back to the client before the client even knows that it needs them. So that's the general idea of the main use case for server push, even though there are other use cases. And then it would send the response. Now, as I said, that's a high-level view. What actually happens is slightly more complicated, which we'll see in the next slide. So it's actually a 2-stage process. What happens first is when the server receives the request, it actually sends push promise frames back to the client saying, okay, I have this resource and I'm going to send it to you unless you say you don't want it. So those push promises that inform the client that that these resources are on the way if you want them. And the client has the opportunity to reset these frames, because you can see each push promise contains a promise stream ID. So it's possible for the client to cancel those or to reset those promise streams if the client doesn't want to receive the data. If the client doesn't do that, then the responses will eventually arrive on the relevant stream. Okay, so that's a real high-level view of HTTP2. So let's go on quickly to the Completable Future API. So basically, Completable Future really is it's a framework for asynchronous programming, but rather than being based on callbacks or that kind of thing, it uses what's known as a continuation style, which is a style of programming that looks somewhat similar to traditional blocking or synchronous code, but while maintaining fully asynchronous capability. I'll define exactly what I mean by that in some examples further on. But in particular, specifically, Completable Future implements the java.util.concurrent.Future interface, which has been around for some time. And it provides a standard API for completion. So it guarantees that a Completable Future object can only be completed once. It can either be completed normally by providing an object of the type that you're expecting, of the result type that you're expecting, or else it'll complete exceptionally with an exceptional or a throwable of some sort. Completable Future also implements the completion stage interface, and this is the interface with a large number of methods that provides this, what I'm describing as the continuation style of programming. And it also implements various static methods for creation of completable futures and ways to create aggregated completable futures, which we'll see in some examples further on. So what can you do with this class? Let's just take a simple example. So let's imagine that we have a method of some class, and the method is called load. It takes a URI. So instead of just blocking and returning some object like a document, this works asynchronously and returns a completable future of document. So when you call load, it just returns immediately. Having started the load operation in the background on a background thread, it returns your completable future object, so what can you do with that? The simplest thing you can do with it is just call get. So that blocks and it effectively emulates traditional blocking behavior, which not very interesting. But when you call that, it blocks and returns the document, or else it will throw an exception. If it throws an exception, that means the completable future completed exceptionally. So let's look at a more interesting example. So let's say we start off the same way. We call this load method, which returns a completable future of document. But what we're going to do here is we're going to add a second stage by calling then apply async, which is a method of completable future. And what that does, it adds a second asynchronous stage to this operation. So you have the first stage, it's the load. And the second stage takes the output of the first stage, which was a document, and it, in this case, in this simple example, it creates an image object, and that's assumed to be something that takes a significant amount of time and is arranged to execute asynchronously. But what you can see, that the return type of this it's no longer a completable future of document, it's now a completable future of image. And that's just a consequence of the way these types are set up. So let's then add a third stage. So in this case, the input to the third stage is the output of the second stage, which was an image. And in this case, we just simply display the image that we have received. And in this case, there's no return value. So the aggregated result of all of this is a completable future of void. So you can see here that it's possible to combine multiple asynchronous operations to create some kind of higher level abstraction that maybe hides some of the details that you're not interested in. At the end of all this, assuming that the completable future, let's say when we call cf.join, which is very similar to the get method, if that doesn't throw an exception, it means that all three of those stages succeeded. If any one of them threw an exception, then that join method would throw an exception, and you could query it to see what the actual exception was. So with that brief introduction to Completable Future, I'll go on to the HTTP API itself. So first I want to just talk a little bit about the status of this work. The API and the implementation are still under active development as part of JDK 9, but we've kind of decided we need a little bit more feedback. Now it's currently integrated in JDK 9, but we're still working on it. What we're considering doing is moving it out of Java SE and into what we're calling an incubator module. Now you probably haven't heard of this before because it's a brand new idea that we're just contemplating. But the idea is that it would remain part of JDK 9, fully visible and usable, but not part of Java SE. And in particular, it wouldn't be a standardized API. There isn't a commitment that it will never change. So the idea would be that the API and the implementation can be used in JDK 9 and then standardized in a following release, hopefully 10. So as I said, this is it's just an idea that's being floated at the moment, or will be soon, but hasn't been widely discussed yet, or certainly not approved. So, but if you're interested in this, I'd keep an eye out for it. One other thing to mention is that up to now, this incubator module idea will have its own specific namespace. So up to now, we've been using java.net.http for this work, but that would be different if it moves into this incubator namespace. So onto the API itself. Well, it's a relatively simple API. These are the list there, are the classes that you will most likely encounter. For a very minimal application, really all you will need will be the HTTP request and its builder class, the HTTP client and its builder, and then the HTTP response. Now there are a number of others which we'll also have a look at. And so the API and the implementation supports both HTTP 1.1 and HTTP 2, but from what we've seen earlier, you would expect the API is mostly agnostic about the version. So let's take a look at a simple example. So building a HTTP request, how do we do that? Well, it follows standard builder pattern. A static method on HTTP request called newBuilder takes a URI and returns an HTTP request.builder object. And then that builder class has various setter type methods which return the same instance, so that you can chain these calls. And then eventually you'll set the request method type and call build, which returns an HTTP request, an immutable HTTP request object. So it should be fairly familiar, I think. So the first example, you can set headers, set the request method or the request type, and then build. Now this example possibly slightly more interesting in that we're doing a post here, so we need to specify a request body. So what we're doing is we're calling some method called fromFile, which takes a path object, and that specifies that the request body is going to come from that file. So the output from this fromFile method is an object of type HTTP request.body processor. Now we'll take a look at that type later on, but it's essentially a type that converts user-defined objects into sequences of byte buffers that the library can send out as part of the request. And this fromFile method, where does it come from? Well, it's a static method in this body processor type. Okay. So let's take an example. Having built a request, how do we send it and receive the response? So let's assume we have a request. We need a client. We need an HTTP client in order to send the request. Requests are sent on HTTP client objects. So one way to create a client is to call HTTP client.new HTTP client. So in this case, we're calling client.send with the request object that we've just created. And the second parameter is a handler object which tells the implementation how to handle the response body. Now in this case we're using an object returned from bodyHandler.asString. This is one of the standard body handler, response body handler types that we define in the API. And that means the response body is treated as a string, and you can see the HTTP response type itself is parameterized with a type T, and that type T is the type of the response body. So with that, then you can then query the status code, and if the status code was 200, then you call response.body, and what you get back is a string. But of course, it doesn't just have to be a string; it can be any type, such as byte array. So if you had specified a body handler as byte array, then HTTP response would be parameterized with a byte array type, and then response.body itself would return a byte array. And we'll see the complete list of standard body handlers that are provided in the API, and then on how to implement your own ones if that's what you want to do. So let's compare so this example was a simple synchronous send. So what happens if we want to do it asynchronously? So the synchronous send method returns an HTTP response of string in this example. If we want to do it asynchronously, then we call send async with exactly the same parameters, and what we get back is a completable future of HTTP response of string. So what can you do with that? Well, as before, you can simply call join, which blocks and waits for the response, or else throws an exception if the completable future completed exceptionally. But maybe what's more interesting would be to see how we can compose something more higher level. So let's start with, from a synchronous point of view, if you have a request and you called client.send, getting back a HTTP response with a path as the body, and then calling response.body, and you return the body object to some higher level. So you can see that if this is the implementation of some method, what you're returning is just the body object, but not the response, because perhaps the higher level is not interested in the response object. So how do you do that asynchronously with Completable Future? It's quite simple, actually. So you start by calling client.send async, and you feed that into .then_apply, which takes the response object output from the first stage and returns the response.body. And you can see the completable future in this case is a completable future of path. So in that case, you're returning a higher level object rather than the HTTP response. So what we're going to do is we're going to take that behavior and wrap a method around it, and then use that in another example. So defined a method called fetchAsync, which takes a URI and an HTTP client and returns a completable future of path, as I've shown already. Just one caveat though, when implementing this kind of code, it's important that if you're mixing traditional blocking code with asynchronous code, and if the blocking code can throw exceptions, it's quite important to actually catch those exceptions inside your method, because you probably want all of your errors to be handled through the Completable Future API, rather than some of them being thrown as exceptions up through the call stack. So it's better to do something like this and catch exceptions that can be thrown at the time when the method is called. And in this case, catching all throwables, return a completable future.failed future, which is a completable future that has already been completed exceptionally with the exception that you've given it. Okay, so let's see what we can do with this fetchAsync method. So in this example, we're going to start with a client and a number of URIs, and we just want to fetch these 3 URIs concurrently. And of course, there's a multitude of different ways to do this, but this just seems like a nice illustration of how to do it. So in this case, we're going to create a stream of the 3 URIs, and then feed that into a collector. And then the collector we're using here is an interesting one, returned from collectors.toMap. And what collectors.toMap does is it takes the stream and produces a map. And the map that it produces is defined by 2 mapping functions that you provide to the toMap method. The first one maps the incoming object type, which are URIs in this case. It maps the URI to the key type of the map, And the second function maps the incoming URIs to the value type of the map. So we're simply using function.identity because the incoming URI is the actual key type that we want. And we're using fetch async, which returns a completable future of path. So what we can see, the resulting map will be a map of URI to completable future of path. So when you execute this code, it will return immediately with your map, and it will be executing the 3 URI loads concurrently. So what do we do next? Okay, so what we want to do is we want to have a single waiting point. So again, there are multiple ways of doing this, but this just is a useful illustration. This is one of the static methods on Completable Future. It's called all_of, and it takes an array of any completable future type and gives you a single aggregated completable future which completes when all of the given completable futures complete either normally or exceptionally. So it's kind of similar to like a network's level select operation for managing multiple connections at the same time. So basically, the completable future void that's returned, which I'm calling all in this case, when you call all.join, if that returns normally, it means that all of the individual URIs were loaded normally. If it throws an exception, it means at least one of them failed, and then you can go back to the map and see which one failed. Okay, so I think that gives a flavor of how this asynchronous API can be used. So we'll just step back and look at the HTTP client class and how it gets configured. It has a very similar builder type of architecture as HTTP client. You call HTTP client.newBuilder, and it returns an HTTP client.builder object. You can set various things like a JavaNet authenticator or SSL parameters, the SSL context or SSL parameters to be used for requests on this client, sent on this client. You can set a proxy, an executor. So this would be this object will be invoked to provide the threads for asynchronous operations that are sent through this client. You can set the redirection policy, and finally, this cookie manager also, that's possible. And then finally, we have a version method which allows you to specify either this must be HTTP1 or you're allowing for the possibility of HTTP2. I didn't mention this earlier, but what's interesting about HTTP2 is that there's no particular additional overhead with speculatively selecting HTTP2 and then falling back to HTTP1. HTTP2 was designed, reasonably well in that respect, in that no additional round trips are required if it turns out you try to do HTTP2 but it falls back to HTTP1. Now there is a small overhead involved in establishing a HTTP2 connection for the first request when it succeeds, but if you're not sure that the server you're talking to talks HTTP2, there's no particular problem with selecting HTTP2 as the version to use anyway. Okay, so just take a little look at the kind of things you can do to a HTTP request when you're building it. You can establish, you can set headers in a number of different ways. The header method just accumulates additional headers using simple name value syntax like that. You can specify timeout using a duration object, and if the response isn't received within that time, then an exception is thrown or the operation completes exceptionally. And as shown earlier, you must specify the request method type, and if it's a post or any type that takes a request body, then you also specify a body. And then finally you call build, which returns the request object itself. So in this example, we're calling client.send Yep, which sends the request and expects a byte array as the response body type. And what about the HTTP response type itself? Well, these are the methods on that interface. So these are the things that you can examine in a response after you've received it. You get the status code, the URI that it was received from, the request that was initially sent and associated, or that generated this response. If redirections occurred, then last request may return a different request to the one that was initially sent. Then you get the SSL parameters, the version that was used. We'll take a look at headers in a moment, and trailers, and then finally type body, which is type T, the parameterized type on the interface itself. Just to take another quick look at the how headers work. So you can see there's a headers and trailers method which return an HTTP headers directly, or in the case of trailers, a completable future of HTTP headers, because it's not always guaranteed when the HTTP response object is available that any trailers will be available at that same time. And then HTTP headers itself is a fairly simple interface with those four methods, which allows you to access headers as single-valued or multi-valued headers. Okay, so to go on to something a little more advanced, we'll just take a quick look at the request and response body processor functions. So as I mentioned earlier, the purpose of these interfaces is simply to convert between user-defined body types and sequences of byte buffers, which is what the library needs to send and receive on the network. And this is based on the java.util.concurrent.Flow API, which has been added recently in JDK 9. I'll give a little description of Flow itself in the next couple of slides, but basically it's a fairly general purpose publish-subscribe mechanism that defines three types: flow.publisher, flow.subscriber, and flow.subscription. And the way it's used in this API is that for request bodies, the processor acts as a publisher and the HTTP implementation acts as a subscriber, so it subscribes to the information that the processor is generating. And for response bodies, it's the other way around. The library is the publisher because it's receiving the data, and the processor is a subscriber to that. So just a brief digression into the Flow API itself. As I mentioned, there's three types, and this should give you an idea of the sequence of events that typically happen when Flow is actually used. So the first thing that happens is a subscriber calls the subscribe method of publisher, or at least a subscriber is provided to a publisher through the subscribe method. So then the publisher immediately calls back to the subscriber, calling its onSubscribe method and providing a subscription object. So what happens next then is, so at this point, we're in a kind of a data transfer phase where the subscriber is allowed to request items from the publisher by calling the request method on the subscription. So this is flow controlled in the sense that there's a window of unfulfilled demand. So this is like a number of items that the publisher is allowed to send to the subscriber. And that's completely under the control of the subscriber. The subscriber must call the request method, which takes an integer parameter, n, say. So if it calls request with the number n, then the publisher is allowed to send n items back to the subscriber. So in other words, the publisher is allowed to call the onNext method of the subscriber n times. So that's kind of how the flow control works. So then, once all of the data has been transferred, the publisher calls onComplete on the subscriber, and that signifies the end of the subscription. If an error occurs, there are two ways. The subscriber can cancel the subscription at any time, or the publisher can signal an error by calling on error on the subscriber. Now, this all looks kind of complicated, and most HTTP applications don't need to know anything about this, but if you're implementing new body processor types, then you need to know about this stuff. So in terms of specification, the request body processor type extends flow.publisher of byte buffer, and it defines one additional method called content length. And if the body processor knows what the content length is, then it can supply this information through this method, and that can be useful to the implementation for setting things like content length, headers, and whatever. So these are the static implementations that the implementation provides. So you can see there, this is the complete list of standard ones. So you can, what that effectively means is that simple applications can send request bodies as strings, byte arrays, from input streams, from a file, or from an iterable of byte arrays, or in certain cases where where no body is required, then there's a method for that. But as I said earlier, you can implement your own by implementing these methods yourself. Now, responses are handled in a two-stage fashion. There's also a body processor which kind of operates in a similar way to the HTTP request.body processor, but there is a higher level body handler also, and this is the object that's actually provided by the caller. And when this method is invoked, it returns a lower level body processor, and I'll explain the rationale for that in a moment with an example. And you can see here the definition of the body handler type. It's a functional interface, which is a single method called apply. So this method will be called as soon as the headers have been received from a response. So it immediately gives you the response code and the headers object, and it allows the application to decide exactly what it wants to do with the body, whether it wants to receive it or not, and exactly where to put it if it does want to receive it. We'll see some examples of that in a few slides. So the response body processor type, it extends flow.subscriber of byte buffer, and it defines one additional method called getBody. And this is this returns a completion stage of type T. So the implementation needs to accumulate the data and do whatever needs to be done to create the T object, whatever the T type is for this processor. That method is the one that needs to know how to create it from the incoming data. And then we provide a similar set of static implementations of both body processor, as what we're looking at here, and also body handler. So these are these are standards. These static implementations, they essentially don't look at the incoming status code or headers. They just simply return the equivalent body processor in all cases. So that's for the simple case where you always want to receive the response body, which would be the normal case. So if you don't want to use one of these predefined body handlers, then the alternative is to write a little lambda like what's shown here. So in this case, we're calling client.send. The first parameter is a request, and the second parameter is this lambda, which takes the status and the HTTP headers and looks at the status and says, well, if the status is not 200, then we don't really want to look at the body, so we're just going to return a body processor that discards throws away the response body and supplies this string error response as a proxy for the actual response body. If status was 200, then we're going to return a normal as string body processor where we treat it as a string, a UTF-8 string. So that's an example of where that behavior can be customized. Okay, so I just want to talk a little bit about the server push API. So how do we handle server pushes? Well, the first two methods you can see here are send and send async, which I've described already. The third one is a second version of send async, which takes a request, but in this, instead of taking a response.body handler, it takes a multiprocessor. So this is an object that knows how to deal with all of the complexities of server push. And you can see here that this method is parameterized with two types, u and t. So t is the same as before. It's the type of the response bodies that you're going to receive from this sequence of server pushes. And so what's u? Well, u is just some aggregate object that has some overall significance for the overall operation. It can be anything, but we think in most common use cases it could be something like a collection or a map of requests to responses, for example. And in fact, we think that case would be so common. We've provided a slightly higher level API that caters for that, and I'll describe that in a moment. But before I do that, let's take a look at the multiprocessor interface itself. So multiprocessor has a number of callbacks. These are just traditional callbacks. So the first one is on request. So on request is called first time for the actual request that the client generated and sent. And then it's called once for each push promise that the server generated and sent back to us. So that gives the client the opportunity to accept or reject each individual push promise. And that's why the return type of that method is actually an optional body handler rather than a body handler. So if the optional is empty, that's telling the implementation, we don't want this server push, just throw it away. The second method then is on response. That's called once for every response that's received. So depending on which pushes were accepted and which were rejected, on response will be called for the main response and for every push promise that was accepted. If an error occurred, instead of on response being called, then on error gets called. So either of on response or on error will be called for every expected response that you are expecting through this interface. So the final method then, this is the method, the finisher method, which allows you to create the U aggregate object. And it actually provides two completable futures as input. So that gives you the opportunity to generate this aggregated object at one of two different times, either after all of the push promises have been received or at the very end when all responses have been received. So the return completable future can be dependent on either one of those two input completable futures. So let's take a look at the simplified interface. Now, it may not look that much simpler in terms of specification, but when it's used, it is quite a bit simpler. So let's go back to the send async method and the type U. So what we're defining here is a value for U, which we're calling multi-map result. And what that is simply a map of HTTP request and completable future HTTP response of V with no additional methods. So that's what this simplified interface is always going to return. So what type of multiprocessor do we need then in order to use that? Well, we've provided a method in multiprocessor, a static method called asMap, and that takes a function. That takes a function which is basically the complexity of server push is distilled down to the implementation of this function. We'll see that in an implementation. So what that function does is it's called with each incoming HTTP request, and it must return an optional body handler for each request. And we'll see now how that works. So a real simple implementation of that is what's shown here. So we're calling client.sendAsync with the request that was created. And the second parameter is multiprocessor.asMap and a lambda that essentially ignores the incoming request. So what we're saying here is we're always, every push promise that comes in, we're always going to return a body handler that treats it as a string. And so at the end of all of that, when we call join, what we have is a multi-map result of string, and we can search through the map and examine any of the requests or any of the parameters of the response object. Okay, now a slightly more complicated example is shown here. So in this case, instead of a one-line lambda, we have maybe 8 lines of code here where we do actually examine the push promises. So in this case, we've decided we're only going to accept push promises that are .html files. So just an arbitrary choice, for example. So we take the incoming push request, we extract the URI, extract the path from the URI. If the path does not end with .html, then we return an optional .empty. So that means we're rejecting this push, we don't want it. Otherwise, we create some kind of a path to store the incoming file and return a response body handler .as file with that path destination. And then that's where the implementation will store the incoming pushed resource. So basically that's pretty much what I want to talk about today. In conclusion, the API, it's relatively easy to use in the common cases, but it does have enough richness to support the less common cases, particularly with server push, and it leverages a lot of the new features that have been defined in JDK 8 and JDK 9. And as I mentioned earlier, the plan or our hope is to include it in JDK 9 as what we're calling an incubator module, which will allow us to, our feeling is that the API is kind of 85–90% complete and ready, but perhaps around the server push area we need a little more experience before we can fully standardize it. And with people using it in JDK 9, we'd hope to standardize it in JDK 10. And finally, the source code is available at the link below if you want to play around with it. Now, it might not, it's still changing a little bit, it might not be 100% mapping to what I've presented there today, but it is mostly the same. We welcome feedback on the emailing list shown, and if it updates to particularly this incubator idea will be announced on the various email lists. Okay, so that's it. Thank you very much.